Start now.
Recording in progress.
Okay, so uh, hello, welcome to the eighth lecture of number theory. Today we will discuss mainly Diophantine equations. But before that, let us just look at two interesting things. The first one is so there is a problem about like if you are given this infinite 2D plane. Okay. Just for clarification, so now we are not doing Diophantine. Now we are just doing some interesting number theory things. First one is if you are given this infinite xy plane, okay, and you have to tile it like you can tile like this now. This is one kind of tiling. All these are tiles. Like this, you have to tile the entire plane. Okay, or you can tile like uh, this also, right? So if I have only been given regular polygons means all their sides are equal and all their angles are also equal, I think. Okay, so if you have been given only regular polygons to tile this entire plane, what are the polygons you can use? Like if I use a square is a regular polygon, na? All sides are equal and all angles are also equal. So square is a regular polygon. So I can tile this infinite plane like this using infinite squares, right? So
Yes,
square is there.
yes.
Square can be used. It is there in my list. What other shapes can I use? This is the question. Regular polygon shapes only. Like I can even use rhombus, but there the angles are not equal, so I am not thinking about it too much right now. Doesn't mean that I can't use it. It's just that my question requires regular polygons. That's why I'm not considering rhombus.
You
Or
can
else,
use equilateral triangles.
yeah, we can use equilateral triangles again.
Pentagon won't work.
Huh?
Pentagon won't work alone.
Okay, pentagon won't work. Very good observation. Like this, you can use triangles. Na? So equilateral triangle is also there in mind.
A hexagon will do.
Hexagon will do. Very good.
Sir,
Pentag
octagon. Sir, octagon.
wait. Pentagon won't work. Hexagon will do. Octagon also you are saying it will do. Acha, but how are you saying all this? Just by symmetry, na? Like you are just analyzing each polygon one at a time and saying whether it can do or not. Like for n equal to 3 triangle you tried. Then for 4 square you tried. Then for 5 pentagon you tried, it did not work. For 6 you tried. So what is your policy? Will you try like this till infinity? Like that is what you are doing, na? Right now, you are just trying new things. Or are you doing something else?
I was trying it.
Trying. Okay. So see, trying is not a very systematic method, but don't underestimate trial and error, because in any problem, if you are not able to do anything else, you should always at least try out things and like try to guess a pattern or something like that. You should get your hands dirty by trying. Okay. So I'm not saying that trying is bad, but I will just tell you a better method. Okay. Like if you don't come up with the better method, then trying is the next best method. So trying is always a method. Don't underestimate trying. But anyway, since we are studying number theory, okay. So why will a pentagon not work? Let us. How are you tiling things? Like when there is a triangle like this, this is the tiling of a triangle, na? Till infinity, everywhere. So this is 60 degree. 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 And this is 60 degree. So what do you see? Like in each vertex, the total sum must be 360 degree, right? That is very obvious. Even in the square case, see it was here 90 degree, 90 degree, 90 degree, 90 degree. So wherever like many polygons meet at one common vertex, there the total angle has to be 360 degree. Okay, so 360 uh, divided by n. This has to be an integer, right?
So like
Then I
each angle must be a vector of 360.
what?
That means each angle has to
That
be a
means
factor
each
of
angle
360.
has to be a factor of 360. Yes. Like 360 by n has to be an integer, and for any regular polygon, if you want it to tile the entire plane, then this angle should be a factor of 360. What is this angle in general, by the way? How
Sir,
much
complete
is it?
angle. Sir, complete angle. Sir, which one, sir?
What?
Sir, which one, sir?
For n-sided polygon, what is the each angle? Regular polygon.
Sir, n minus 2
Sir,
into
n
180
minus 2
degree by
into
n.
180 degree by n. N minus 2 into 180 degree by n.
Yes, sir. Yes, sir.
Yeah. Okay. So if I open this, I can write this as n into 180 degree by n minus 2 into 180 degree by n. Right. So this can
Yes,
be
sir.
written as 180 degree minus 360 degree by n. Okay. So this is integer only. I just need this to be an integer. Then I can stack n of them and it will form a complete. Not exactly the angle. Wait, I forget this. The previous argument only was correct. Just 360 by n has to be an integer. Then you can stack n shapes like this. 1, 2, 3, 4, n like this. Okay. So, for example, in the hexagon, in the equilateral triangle case, here n is not 3, here n equal to 6, because I am repeating 6 shapes. See, 1, 2, 3, 4, 5, 6. So, if I am stacking 6 tiles, then 360 by n has to be an integer, like this. So what are the factors of 360? 1, 2, 3, 4. You can find out the factors now. So do you understand what to do next? How to approach this? Like one case is redundant, you can't do anything because we only want regular polygons. Two is also useless. For three, we can put three hexagons like this. So this is the n equal to 3 case. We have one hexagon, two hexagon, three hexagon, three regular polygons, and so on. Like you have to do this for all the factors of 360 and you will get all possible shapes. You don't have to do any trial and error. But you can just take all possible cases. So homework is find all these shapes. Okay, so those who joined just now, I just finished a question. You can watch the recording for that. Uh, Now I'm starting a new one. Okay. So now the question is, uh, can there be a polynomial that always outputs prime numbers? For integer inputs. Like, see, f1 equal to some prime, f2 is some other prime, and so on. Like, whatever number you put, you will get a prime number only. This may not be the first prime, second prime, like that. Like, it may be the case that f1 is 37, f2 is 3, f3 is 23, okay, f4 is 2. Like the order does not matter. We just need prime outputs. Is it possible? This is the question.
I think it
Where
isn't. I think it isn't.
okay, tell me your logic. Polynomial with integer coefficients. Did you guess or do you have a proof?
Just a guess.
Okay,
Just a guess.
okay. So yeah, like it seems like you can't actually. And remember what I said in our first class on induction. When you don't have any direct way to prove, you try contradiction, you try induction, you try these things. When you try these things, when you don't have a direct way to prove. So as Sabyasachi guessed, he guessed because he could not find a direct way. Even I cannot find a direct way. So let us do this proof by contradiction. Okay, just a minute. So let us assume that fx is a polynomial. Actually, it need not be with integer coefficients. Actually, no, it has to be. Hmm. Okay, polynomial with integer coefficients such that if n is always a prime for integer n. This is our assumption. We will prove this wrong using contradiction. Okay. So for some integer u, say if u is p, where p is a prime. Okay. So now we will study this object f of u plus p. Okay. So there are actually two ways to do it. Both are similar. First one is fx equal to a naught plus a1 x plus a2 x square till an next to power n. Okay. So f of u plus p equal to, you can write it, f of u is just p. Okay. So f of u plus p minus f of u. What can you say about this? Isn't it divisible by p? Huh? Wait, let me just take a small example. Say fx is x square plus x plus 3. X square plus 2x plus 3. Okay. So f of u plus p equal to u plus p whole square plus 2 into u plus p plus 3. F of u equal to p. Now if you, no, f of, wait, not p, don't write it p, write the whole expansion. Huh.
Sir,
F
both
of
are
u,
P. Sir,
wait,
both are
wait.
P.
No, what? What? No, both are not p.
No, that P is same to same as
That P is
f of
same
u
to
is equal to
same
P.
as f of u is equal. Yeah, that p only I have taken.
Okay, sir.
Now if you subtract,
Okay,
see
sir.
f of u plus p minus f of u, how much is this? U plus p whole square minus u square. What is this? This is u plus p plus
Sir, 2P
u
plus P
plus.
square. Sir, 2P plus P square.
Okay, plus 2p, right?
Yes, sir.
So this is divisible by p, na, 2u
Yes, sir.
plus p plus 2. So it is divisible by p. But like I took an example, you have to prove this in general. You can use this identity a to the power n minus b to the power n equal to a minus b times जो भी है, it is divisible by a minus b. That is the main thing we want. So homework is prove it yourself. Prove that p divides f of u plus p minus f of u. You have to prove it, homework. Okay. So if p divides f of u plus p minus f of u, then f of u plus p minus f of u is pk na, for some integer k.
Yes, sir. Yes, sir.
So f of u plus p equal to pk plus fu. Now fu is p. Remember, that is what we took. So this becomes p into k plus 1. Okay. If k not 0, then f of u plus p is composite. Agreed? If k equal to 0, then k plus 1 is 1. and f of u plus p is again p, which is a prime. But if k is not 0, then f of u plus p is composite. Na? So our assumption was false. We have not fully proved it, but if k is not 0, then we have proved it. Everyone is okay with this?
Yes, sir. Yes, sir.
Okay. Now, what if k equal to 0? That is the main question which is disturbing us, and for which the proof is not yet complete. Okay. So, see, f of u plus p minus fu is divisible by p, but p also divides f of u plus 2p minus fu, or f of 3p minus fu, or anything like that. In general, p divides f of u plus np minus fu for n, all n in integers. Okay, this also you prove at home using that identity a to the power n minus b to the power n. Simple proof. So if f of u plus p equal to p, then try f of u plus 2p. Okay, you have infinite choices, na? F of u plus 2p, f of u plus 3p. You can try on. Like, if this is also p, then try the next one. If that is also p, then try the next one. Okay. Now still there is one problem remaining. What if f of u plus kp equal to p always for all k? Okay. So then basically what they are saying is, there is a polynomial. This is p. No, wait. This is u. This is u plus p. This is u plus 2p. This is u plus 3p. This is u plus 4p. U plus 5p, and so on forever. Okay. F of, and this is suppose p. Let me draw a line. So this is the graph of the polynomial I am going to draw. So f of u is how much? P. F of u plus p is also p. F of u plus 2p is also p. Acha, meeting is ending in 10 minutes. F of u plus 3p is also p. All of them are p, na?
Yes, sir. Yes,
So
sir.
now if you consider the polynomial gx equal to fx minus p. Okay. What are the roots of gx? What are the roots of gx? I mean, when is gx equal to 0?
Sir, when f of x is equal to p.
Yeah, so when is that? For u, u plus p, u plus 2p, and so on, right?
Yes, sir. Yes, sir.
X equal to these values. So there are infinite values, na?
Yes, sir.
Infinite
Yes, sir.
roots of gx. Okay. But by definition, a polynomial can only have finite roots. Because, like, see, even sin x has infinite roots at 0, pi, 2pi, and so on. But sin x is not a polynomial. Polynomial can behave like sin x for a while, but then it has to at some point like become a polynomial, go to infinity or something. It cannot forever have roots, infinite roots. Polynomial, wait, every polynomial has finite number of roots. This is by definition. Okay. So this cannot happen. Ki for all this scenario is basically impossible. Okay, agreed? Because if it was possible, then a polynomial needs to have infinite roots, but a polynomial cannot have infinite roots. So this situation is not possible. Okay. So if this situation is not possible, then I will definitely find some u plus 5p or u plus 50p or some number u plus np for which f of u plus that number is not p. Okay. So for that it will again be k will not be 0 and this thing will become composite. Okay. So what was our initial assumption? Initial assumption was always prime output. But we have here produced f some f of u plus kp for which it is of the form p into k plus 1 and k is not 0. So this thing is definitely composite. And if this thing is composite, our assumption was wrong. Our assumption was wrong. Hence proved by contradiction. So what did we just prove? That a polynomial cannot always output prime numbers. Okay. And here is a nice lemma which you can prove at home and also use. If fx is a polynomial with integer coefficients, then for all integers a, f of a plus fa is a multiple of a. Okay. This is a lemma which we used in this question. Here f of u was p. So that's why we used f of u plus p, u plus 2p and so on. Okay.
Sir, can you please
So now
send
let
this
us
homework in the group? Can you please send this homework in the group?
uh okay, but like copy it down now only.
Okay, sir. Sir, could you please keep it for a
Okay,
while? Sir, could you please
Yeah.
keep it for a while?
And anyways, like I think the meeting is going to end. So let us see. After you have copied, tell me. I will start Diophantine in the new meeting. So let us continue our discussion. Let us continue our discussion on Diophantine equations. which is the final, almost final topic in number theory, which we will study. So first, all of you remember the example we did last time, na? We took some mod 6 and we found that there is no solution for that. A mod 16. That n to the power 4 is always congruent to 1 mod 16 if n is odd, and 0 mod 16 if n is even. And then x to the power 4 plus y to the power 4 plus z to the power 4 plus w to the power 4 equal to 2021. But this is 5 mod 16. This can be at most 4 mod 16 if all of them are odd. If even one of them is even, then it can be 3 mod 16, 2 mod 16, anything. But it cannot be ever 5 mod 16. So LHS and RHS cannot be equal, no solution. Remember this, na? So let us do a
Yes, sir.
similar example. This is from RMO 2018. This is the paper in which I appeared actually. And Snehin Bhaiya got full marks, 102 out of 102. No, actually, I think this is 2017, not 18.
Sir, you gave in 2017.
Snehin also.
Okay.
I was in class 10, he was in 11. He got full marks. I got 53 or something. Passing marks was 51, so I passed.
51.
Something like that. Why?
Sir, it is too much.
Exactly.
Oh, 30. Only 30 people passed, na, from West Bengal, entire West Bengal. Also, that year paper was a bit easy. Like the next year, the cutoff went in 40, 42, like that. So it varies year to year, and that year the paper was easier, so cutoff also was higher. Next year only cutoff went lower because paper was harder. You can see IMO paper 2017. It was very easy. Matlab, there was a question on polynomials. Okay, that can be solved by anyone in school also. It was so easy. You just have to put the value, subtract, ho gaya. Like whatever has been asked to prove can be just directly proved. You don't have to think anything. Just prove it. So 17 marks वहीं पे मिल गया. Now you have to do 2 more to pass. That is hard, but like that every year you have to do 2 to 3 sums minimum. Anyways, let us get back to the question. Show that AQ plus A plus 1 cube plus A plus 2 cube plus A plus 3 cube has no solutions in integers A comma B. Okay. So you have to proceed like this only. Here we took mod 16. Here you have to use mod 7. Use mod 7. Okay. And why will you use mod 7? Because like see there are 7 consecutive numbers, and See, there is no very good logic to this. You have to like that's why it's a hard question. You have to think like
Sir, hello, sir.
Yeah, I think I've done this. The main thing to do here is to just expand the LHS and show that there's a factor of 7, and which doesn't have on the LHS, so there's no solution.
Sir,
Problem হচ্ছে network. Yes, not. I guess.
sir, I couldn't hear why you said to use mod 7. Could you please explain it once? I got disconnected.
He himself isn't there, I guess.
Is he disconnected?
Maybe.
Okay.
so till where did you listen?
Still use mod 7.
Okay. So what I said is कि once you know you have to use mod 7, the question becomes easier, na? Like even here, if I would directly tell you solve this, for integers. You don't know what to do. But once I tell you about this nice property that mod 16 has only two values, then you can just apply it here and say that there is no solution. The question becomes a lot easier. So here also, like, this is an RMO question. It's supposed to be hard. And
Sir,
why
I have
you got
almost solved it. Could you please
Sir,
wait
I
for a
have
moment?
almost solved it. Could you please wait for a
What?
moment?
Sir, I have
Hello?
solved the problem almost.
Sir, I
Yes, sir.
solved the problem almost. Not
Yes,
now,
sir.
please. I have to move ahead. You write it and send it to Saptaswa.
Okay, sir.
Huh.
Okay, sir.
So, like, once you know you have to use mod 7, you can solve it. It becomes a lot easier. But knowing that you have to use mod 7, that is where the actual hardness of this question is. And that's why it is an RMO question and it is a hard question, because knowing that you have to use mod 7, this needs a lot of creativity, experience, blah blah blah. Like, the more you solve questions like this, more you have an idea what to use when. Like, here you have 7 consecutive integers, so maybe 7 is a good idea. Like, you have to try out different things and see what is working. There is no rule for that will fit everyone. You have to be creative, you have to experiment, you have to try out things. So now, like, these were equations where we use modular arithmetic. Nah, modulo. We use modulo to show that there is no solution. But this is just one type of questions. Like, there can be a lot of types of Diophantine equations. And let us discuss this question which came in DRMO of the same year. Read the question, please, everyone. Everyone, tell me after you have read it. Have you read it, everyone? Hello, hello.
Yes, sir. Yes, sir.
Okay. So, what is, like, what do you have to do? Tell me. Just like this is a like a story sum. Just tell me the mathematical version. This is in English, na?
Sir,
Tell.
sir, we can consider the number of pens. We can consider the number of pens. Sir, my voice is resounding. Could you please
Sir, my
disconnect?
voice is resounding.
Could you please disconnect
Uh,
your audio from the other device? Your audio from the other device.
Yeah, it's muted only, and also it is not resounding for me. It's for you only, I think. So you can
Yes,
continue.
sir. Okay, sir. So, sir, if I consider the number of pens as
If I consider
X
the number of
and
pens as
the
X
number of notebooks
and
as
the
Y,
number of notebooks as Y,
so sir, 11x plus 13y
11x
is
plus
equal to
13y
1000.
is equal to 1000. Yeah. So in school you have learned how to solve linear equation in two variables, but you needed two equations for that. Here you have only one equation and two variables. What will you do now? And what you have to do? What is your final objective? What do you want to do with this equation?
Sir, we have to find pairs of x comma
Sir,
y.
we have to find pairs of x
Means
comma
the
y.
number of pair.
X comma y both are natural numbers. Only those kind of pairs.
Yes, sir.
Because otherwise they
Yes,
are
sir.
infinite.
So they can be counted. So X and Y have
They
to be
can be
natural number.
counted. So X and Y have to
Ah,
be natural.
okay, very good. Wait, just a minute. So everyone can see this now. I have plotted 11x plus 13y equal to 1000 here. Okay. Everyone can see the graph?
Yes, sir.
Okay. So now what we have to do, this line passes through infinite points actually. Right. This line passes through infinite points. But wait, I don't know. Huh. See, but we have to find points like this. Okay. Uh, see 85,5. This is an integer point. See these points are all decimal, 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 decimal. Here also see. For 86 it is 4.154. Then for 4 it is 86 point something. These are not integers. Now here 86.5 is a perfect point. But you have to find points like this. How many points on this line are like this? That is your question. So, like I showed the graph just for fun. In exam, you won't get Desmos, obviously, but it's nice to use Desmos and build intuition at home. Don't use it to solve questions, but for building intuition, it is a great tool. And use Desmos, okay, at home, like not as I said, not for solving questions, but for seeing things, visualizing maths basically. So, how
Sir,
can we
I have,
approach?
sir,
Sir,
can I tell my approach, sir?
Can I tell my
yeah,
approach,
tell
sir?
your approach.
Sir, I got 11x
Sir,
plus
I got
13y is equal to
11x plus
1000,
13y is equal to
where
1000,
x comma y
where
belongs to
x
natural
comma
number.
y belongs to natural numbers.
So, sir, x is
So, sir,
x is
equal
x
to
is 1000 minus
equal to
13y by
1000 minus
11.
13y by 11.
So, sir, that means as x is
So,
a
sir,
natural
that means
number,
as x
therefore
is a natural number,
1000
therefore
minus 13y
1000
is
minus
is
13y
congruent to 0 mod
is
11.
congruent to 0 mod 11.
X equal to 1000 minus 13y by 11. After that, what you said? X
The
is natural.
1000, the
1000. Yes, sir.
So, what modulo you said? Tell me once.
sir, 1000 minus
Sir,
13y
1000 minus 13y
13y.
is congruent to
is
0
congruent to 0
Okay. So, 1000 is
sir, is
congruent to.
congruent
sir, is
13y
congruent
mod 11.
13y mod
Huh.
11.
So, sir, as y is also a
So, sir,
natural
as
number,
y is also a natural
therefore
number, therefore
13y we can
13y
divide
we can
13y as
divide
11y plus
13y as
2y.
11y plus 2y.
Okay.
So, sir, that means
So, sir, that
1000 is
means
congruent to
1000 is congruent to
2y mod 11.
2y mod 11.
Uh, wait, I'm not sure I followed that.
So sir, as 11 and 1000 they are relatively prime. So sir, 5000 is congruent to y mod 11.
Okay.
Sir, sorry, 500, sir, 500, not 500, sir, 500, not 5.
Hmm.
So sir, now y's maximum value can be when x is equal to 1.
Okay. So what is that y max?
So sir, it will be 989 by 13.
That is how much approx?
Sir, just a minute.
Use a calculator.
Sir, it is almost sir, 76.
Okay.
Maximum it can be 70.
Okay. Now.
Sir, sir, now 5 as we got 500 is congruent to y mod 11. Now sir, we can find different values of
Yeah.
y. So sir, that
But
only I was finding.
you have to check 76 values na by hand, right?
Yes, sir.
Okay.
Sir, like we can also do it like 500 by 11. Sir, y's minimum value can be
1.
5. Sir, 5.
Okay.
Sir, as 500 by 11,
No,
500
like what?
y 500 y 500.
You have to basically check from 5 to 76. You have to check all values of y na by hand.
Yes, sir.
Okay. Okay. Like this is a correct method, but you can't do it in an exam hall because you can't check so many values. But this is a perfectly correct method. I will just tell you a very short method, which is like uh, you still have to check some values, but not so many. Okay, so as Sukrit pointed out that the smallest value of y is 5. You can try this 11x plus 13y equal to 1000. Okay, so for x, y, you make a table for y equal to 1, 2, 3, 4, 5 and so on. Okay, the x values you will get, that is not an integer, not an integer, not an integer, not an integer. Suddenly I think you will get 85, na? Which is an integer. So 11 into 85 plus 13 into 5. This is equal to 1000. This is our first solution which we obtained using trial and error. Okay. Everyone understood till here? We just found the minimum y using trial and error. Okay. You just have to check 5 values. That is not much calculation. Now what you do? See, the sum has to be 1000 and 11x. Wait. So 85. Suppose this is x naught and 5. Suppose this is y naught. So 11x naught plus 5y naught equal to 1000. Now 11 x naught minus 11m plus 13n. Okay, this is not 5y naught, this is 13y naught. And you people are not correcting me, which is, means you are not paying attention. Okay, like what I mean is, from here if you could take 11 common, you would get x naught uh, minus m, and from here if you take 13 common you will get y naught plus n, and the sum will be 1000. So I can call this x1, this y1, then 11x1 plus 13y1. That also would have been 1000, na? Basically, I am adding and subtracting things so that I can take 11 and 13 common and make these new solutions. Okay. Now this thing needs to cancel perfectly, obviously. So uh, 13n minus 11m, this equal to 0. Okay. So 13n equal to 11m. So n divides 11. No. Wait. This is 13 divides m and 11 divides n. Na?
Yes, sir. Yes, sir.
Because these are primes. 11 and 13 are primes.
So they are relatively primes also. So
Yeah.
that's why.
Okay. So this holds true. So what if I just add and subtract LCM, like 11 into 13 is the LCM, na? LCM of 11 and 13 is 11 into 13. How much is that? 143, right? Huh. Yeah. Meeting is ending in 10 minutes. Rejoin after that. So 11 into 85 plus 13 into 5. This was 1000. Now 11 into 85 plus 143 minus, not plus, that will exceed our thing. Minus 143 plus 143 plus 13 into 5. How much is this? This thing cancels. The rest is 1000. So the total sum is also 1000. Now here if I take 11 common, then I will get 85 minus 13. Now here if I take 13 common, then I will get 5 plus 11. This is 1000. So 11 into 72 plus 13 into 16 is 1000. So 72 comma 16 is my new solution. Everyone agreed?
Yes, sir. Yes, sir.
Okay. So now if I repeat this again, first solution was 85 comma 5. This is my second solution. What will be the third solution? Tell me quickly. Not so much calculation. What happens when I add and subtract the
59
LCM?
and sir 59 and 27. Sir 59 and 27.
Uh, yeah. Okay, so what happens when I add and subtract the LCM? From the 11 term, 13 is subtracted, and from the 13 term, 11 is added. And you can verify this will happen always, not only for this case. So how many solutions are like this? What is the next solution?
Sir
This
46 and 38. 46 and
59
38.
minus 13, 46, and 27 plus 11 is 38. Okay, what is
Are
the
there
next
seven
solution?
solutions? Are there seven solutions?
Sir, can I tell something? Sir, can I
Yeah,
tell
tell.
something? Sir, can we also find it using like I was telling, sir, which I was telling, y minimum will be 5. Y minimum will be 5. And sir, 1000 minus 13y has to be divisible by 11. So sir, that means if 5 is the minimum value, then sir, the next value will also be 16.
Why?
So, sir, which you did. Sir, for
Ah,
y,
okay.
sir, y is value. Sir, for y,
Okay,
sir,
okay.
y is value. So, sir,
Like
in
there
that
is no
way,
one method.
so
Na,
sir,
you can
in
do
that
it
way,
like that also. Yeah, you are right.
so sir, like we can form a general term for each term for y, which is 5 plus 11d,
Yeah. That is exactly what we are doing now. So next
Yes,
solution
sir.
is 49 and here
Yes, sir.
33, right? Then what is the next solution? 20 comma mm, 60. Am I right? Someone please do the calculations.
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Okay,
Yes,
and
sir.
what is the this is 5, this is 6. And what is the solution? 71. This is the 7. Okay. Now if you go before this, then y will become negative. And if you go after this, then x will become negative. And you can't buy negative number of pens or notebooks. So we only have these 7 solutions. Okay. So what we did is we used divisibility, na? Divisibility, LCM, all these we used here. Everyone understood this solution?
Yes, sir.
Like I am teaching
Yes,
you
sir.
these methods not because questions like these will come up. Okay. What has come once may not come ever again. You have to make your own methods like this in new questions. I'm just giving you some what has come earlier. I don't know what will come next. You have to you have to develop ability to make these methods. You just like don't expect that equations like this will come. I will solve using this method. That won't help you. What will help you is understand divisibility, understand modulo, understand the basics, and use them to make your own methods. Like this method, this was made by me. Okay. The mod 7 method that was written in RMO solution only, I copied from there. But this LCM method, this was made by me. So like you have to make your own method. You can't or else you can't solve new questions. You will only be stuck with old questions.
Can you once again explain the part where you took
Can you
n,
once again
x naught and y
explain the
naught?
part where you took x naught and y
Ah,
naught?
so wait, let me explain fresh only. 11 x naught plus 13 y naught is 1000. X naught y naught is one of our solutions. Okay. Now if I do 11 x naught plus minus 143 plus 143 plus 13 y naught. If I take 11 common, then x naught minus 13 y naught plus 11. So this I can call x1, this I can call y1. These are my new solutions. Such that 11x1 plus 13y1 equal to 1000. So I added and subtracted here 143 because 143 I can take 11 also I can take common from 143. 13 also I can take common from 143. Basically I had to find a number from which I can take common both 11 and 13 and leave integers as quotients and no remainders. So that I can take common and form new solutions. That was my idea. Okay. Okay.
Yeah.
Right. Okay. So now let us look at another method. This I think is the most common method, and I have even made a handout on this. You should read that and solve the questions. Not S. Factorization. Okay, so factorization is basically you use fundamental theorem of arithmetic and plus algebraic factorization plus trial and error, or not trial and error, casework, or whatever you want to call it. Let us see an example that will make things clear. Let me open an example. Uh, so this came in RMO 1992, and just for fun, let me change the ink color again. Find all integers n such that n square plus 19n plus 92 is the square of an integer. Okay, then tell me the steps. Wait, just a minute. What will you do?
First, you
Complete.
take an integer k for which this expression is a whole square. N square plus 19 and plus 92 is equal to k. K square,
Wait,
sorry.
n plus 92 equal to k square. Okay.
Then we'll multiply the whole equation by 4. So we
4
get
n
10 square plus 76 plus, just a second, 368 is equal to 4k square.
okay.
Now that implies 2n plus 19 whole square plus 7 is equal to 4m square.
4k square.
Yeah, k square, sorry.
Huh.
Yeah, then we will take it to the 4k, we will bring 4k means 4k square minus 2n plus 19 square is equal to 7. Now we can
Wait.
factor
So 2k whole
2k
square.
plus 2n plus 19 into 2k minus 2n minus 19 is equal to 7. Now factors of 7 are 1 comma 7, 7 comma 1, minus 1 comma minus 7, minus 7 comma minus 1. Now we can see for each case, and after that I haven't solved.
Yeah, very good. That is exactly my method. Thanks for telling me and saving the trouble. Okay. So basically, till here everyone understood, na? We just factorized,
Yes,
multiplied by
sir.
4 and factorized. Okay. So after this, what we do? 7 equal to A into B. Find all AB integer. Okay. What are the possibilities?
1 comma 7, 7 comma 1, minus 7 comma minus 1, 7 comma minus 1, and we'll check for each case
1
separately.
7 comma 1 minus 7 comma minus 1
I
and
got that
minus
minus 8 or minus 11.
minus 8. Yeah, perfect. Okay, so these are all the possible cases. Okay, so now what you do, you check these, like 2k plus 2n plus 19 equal to A. 2k minus 2n minus 19 equal to b. Now put these values of a comma b one at a time, and you will get 4 systems. You from there you get all the solutions. So this I think you can do at home homework. Just put these values and see. You will eventually get n equal to minus 8 and minus 11. His homework is obtain this. Put the a b values in these equations and solve 4 times. And bring these values. That is your homework. But like
Sir, I
that,
For
have
the
got
second
it.
one is minus
uh,
8 and the first one is minus 11.
yeah, minus 8 and minus 11. Supreet, you were saying something?
Sir, I have got the values. Like what Spondon sir told, and that way only I did.
স্পন্দন তো স্যার হয়ে গেল ঠিক আছে
Sir, not sir also.
স্যার আমিও স্যার স্পন্দনও স্যার সবাই স্যার হ্যালো
I am literally 1 year elder to him only.
अरे ऐसा मत करो यार
Okay,
okay
sir.
anyway all of you solved it but people who are watching the recording also do this at home don't skip
A
so
similar
main
sum
part
was given in the POTD someday, I don't remember.
oh acha. So, like the moral of the story is, if you can factorize like this, you can just exhaustively find all the possible combinations, try all these combinations using trial and error, and see which ones work, which ones don't work, which gives what solution. List all the solutions. Done. This is basically how we go about factorization. Uh, so my next example.
This was a RMO question.
Yeah.
Wasn't it too easy for that?
But it's from 1990s, so then this was only tough back then. Like now you have all these questions, all the books have been published, Olympiad awareness is there, and you have maths club and all. So like you know the theory, you you studied, but during those times, even this was new, na. Once it has appeared in an exam, everybody studies that. But before the exam, nobody studies it. Na? You understand? Like even in 2000s and all, in JE Advanced, okay, there used to be questions like this. Ki, there is a pulley. This is M1. This is M2. Now solve this system. Like these questions come in boards now. But back then, this was only JE question. Once it has come in an exam, everybody studies it. Ki it may come again, but that will not come again. New questions will come. This is where people left their preparation. You don't have to just know whatever has come. You have to have the creativity to solve new questions. That is where you are better than the rest. Just knowing previous year question, it helps, but it is not enough. You have to develop ability to think creatively. Maths is all about creativity, okay? Maths is not about following rules and all. Maths is about creativity, and school destroys that notion like anything. That's why we created Maths Club. Because in school, what you do, you like, suppose you have a question, you have to apply this rule, apply that rule, apply this rule, da.
In school, so all the questions come from RSA book, nothing to study extra.
In school, like creativity is not promoted. Na, you have a standard book. You have those few questions only that will come in the exam. You solve the book entirely, you will get full in exam. There is nothing to think about. Huh. Even the questions like the methods are already taught in examples. You have to just reapply them. Nothing new. You have to think yourself. It's like following rules basically. But actual maths is not like that. In actual maths, like following rules will only allow you to solve problems which have already been solved. Na? Where do these rules come from? These rules come from people who have already solved it. If I solve a question today and I publish that, then all of you can read the solution and you know how to solve this question. But what is maths? Maths is solving new questions, not resolving old question again and again. What will you do by solving my question? I have already solved it. If you want to solve your own new question, then you have to have creativity. That is the main thing. Okay, so I got diverted from that topic. Homework, n square plus 96 is a perfect square. Find all integers and okay. Again, n square plus 96 equal to k square you take, then you will get k square minus n square equal to 96. 96 is 32 into 3. This is the factorization. Okay. Now you have to k plus n into k minus n. This has to be 2 to the power 5 into 3 to the power 1. Now you have to try all the cases. Okay. So here what I wanted to say, one important thing is, if k plus n is even, then what is k minus n? K minus n is nothing but
And
k
it is also
plus
even.
n minus 2n, right?
Yes, sir.
So, so this is even, this is even. Even minus even, k minus n is also even. And if k plus n is odd, then k minus n is also odd. This also you can show easily. Okay. Basically, in this factorization, both are of the same parity. Parity means odd or even thing. Okay. Parity because like pair, odd and even. Like mod 2. That's why parity. That is the word we use. So basically k plus n, k minus n, these are either both odd or both even. Now if these are both odd, then this factorization cannot be achieved, na? Because there is a 2 to the power 5 here. So this is not possible. K plus n equal to 32, k minus n equal to 3. This case is invalid. Why is it invalid? Because one is odd, one is even. If you solve, you will get k and n, you will get fractions. So you can check that this is invalid. Really, this is invalid. I'm just telling you these things because maybe you will use them in problems. These little things, if you keep in mind, it may help you someday in some problem. So factorize this and find all the solutions. I'm telling you the answer also, just that you can check. 2, 5, 10, 23. But solve the question fully. And I am removing this. Okay. So the next question. is so like how do you approach this? Obviously means how
by
will you
the
approach?
quadratic formula.
But like by contradiction, na? Like you find the solution and then you show that the solution is not interior, something like this.
Yes, sir.
Okay, but there is a number theory method also. I'm just showing you that. Okay, assume
Can just wait a minute.
अरे तू yourself बोल विश्वास था अच्छा I will give you lots of homeworks after the class, so please let me continue because like I have two more things to cover and I need a bit time for that. So from here n square is, if I take minus 7 common, uh, not n plus 2q square plus 2. Okay. Right. Yes. So 7 divides n square, na? Everyone agrees?
Yes, sir.
Okay, and 7 is a prime. So 7 divides n. This we proved in that one of the lectures, na? Not proved, I gave homework. I told you the
So assume
property
n is
that
7k or something, then it's off.
yeah. So if n equal to 7 and 1, okay, then n square plus
It's 0 mod
7n
7 and
minus
2n square plus 2 mod 7, so no solution.
yeah. I can write this as 49 n1 square plus 49 n1 equal to 14 into q square plus 1. Okay. Now if I cancel, I will get 7 n1 square plus 7 n1 equal to 2 into q square plus 1. So again, see 7 divides 2q square plus 1 and 7 is a prime. 7 does not divide 2, so 7 divides q square plus 1. Okay. So q square plus 1 is congruent to 0 mod 7. Q square is congruent to 6 mod 7. Okay. But like for any integer, q square cannot be 6 mod 7. This you can verify. Okay. Just like remember I gave a question that any n square is always congruent to 0 or 1 mod 4. There it cannot be 2 mod 4 or 3 mod 4. It is not possible. Like when you square an integer, these cases get eliminated. So similarly, 6 mod 7 also can never happen. This you can confirm, prove it homework. Prove that this is not possible. Okay. So there exists no solution. Okay.
Sir, could you please scroll up the page?
Oh.
Sir, a bit more just. Yes, sir.
Can you once again explain what you did of the modular part? Means q square plus 1 is congruent to 0 mod 7 after that.
So q square is congruent to 6 mod 7, na? That you got.
Wait, can you
Matlab,
explain that part again once?
हाँ,
Means
wait.
q square plus 1 is congruent to 0 mod 7.
This till here you got.
Yeah.
So q square is congruent to minus 1 mod 7.
Yeah, that is 6 again.
So that is congruent to 6 mod 7.
Yeah, after that, what you did?
So after that is homework. So you have to prove that this can never happen. Like, see, pick any, wait, see, n square. So make a table. 1, 2, 3, 4, 5, 6, 7, 8, till 10. Let's
So we
say.
show the last digits of the squares and then we show that none of them is 6.
No, last digit is mod 10, na? For mod 7, you can't use last digit. Wait, I'm telling you. Wait. 36, 49, 64, 81, 100. Okay. N square mod 4. For now, I'm just doing mod 4 because it's easier to calculate. How much is 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, and so on. See, means this I'm just showing you a pattern, but actually you can prove it, and I gave it in a homework in a previous class that for any integer n square is congruent to 0 or 1 mod 4. Okay. So it cannot be 2 mod 4. It cannot be 3 mod 4. 4 mod 4 is just 0 mod 4. Similarly, you have to show that q square can never be 6 mod 7. This is not possible. And if this is not possible, then our assumption was wrong, so hence proved by contradiction. You have to just show that this is not possible. That is your homework. Now, let us study this very famous and beloved thing. So basically the question is find all integer solutions to x square plus y square equal to z square. This is the Pythagoras theorem. So basically you have to find all integer triplets which satisfy Pythagoras theorem. So let us observe one thing. You all know 3, 4, 5 is a Pythagorean triplet. Right.
Yes, sir.
3 square plus 4 square equal to 5 square. You all know 6, 8, 10 is a Pythagorean triplet. But 6 is 2 into 3. 8 is 2 into 4. And 10 is 2 into 5. Okay. So, see, in this equation, 3 square plus 4 square equal to 5 square. Now if I multiply this by 4, this entire equation if I multiply by 4, what will I get? 2 square into 3 square plus 2 square into 4 square equal to 2 square into 5 square. Now if I what is this? 2 into 3 whole square na? So 6 square plus 8 square equal to 10 square. Similarly, if I multiply this entire equation by 9, what is the triplet I will get? 9, 12, 15. This also satisfies Pythagoras theorem. So if A, B, C uh, is a Pythagorean triplet, then Na, Nb, Nc is also na, because the n square will just cancel from LHS RHS. Understood?
Yes, sir.
Acha. So like if you have this basic if I call this basic, so if you have this basic solution, you can generate infinite solutions using just multiplying integers with the basic solution, right? So I will here just mm, uh, calculate the basic solutions, because other solutions are just multiples of basic that you can generate. Okay. Okay, so basically what does basic mean? Wait, this color is annoying me for some reason. So I will find solutions of this form. For example, here you see 3, 4, 5. What is the HCF or GCD of 3, 4, 5? 1. Or 5, 12, 13 is also another Pythagorean tip. Here also HCF is 1. So I will find, see, so this is my modified question. Find A, B, C such that this is my modified question. Another note is that in maths, sometimes when you are solving a hard question and you cannot solve the question directly, you may solve a similar question and that solution can help you in solving the original question. So that is exactly what we are doing here. I am saying that you can generate infinite solutions by just multiplying ABC with n. So I am just solving this special case where HCF is 1, because other cases I don't need to solve. So you can modify the actual question while solving and then use that to solve the actual question. That also happens in maths problems. Okay. Okay. So, acha, by the way, parity is just mod 2. Like, you check na, in Diophantine equation, suppose LHS is coming odd, RHS is coming even. So this is 1 mod 2, this is 0 mod 2. Acha, so odd number cannot be equal to even number, so no solution you say. But like why only odd even? Like if odd even is not helping, maybe mod 3 will work, maybe mod 7 will work, mod 16 may work. Like odd even is just mod 2. It's a special case. There is nothing special about mod 2. So like don't restrict yourself to odd even because you have learned modular arithmetic now, so you can use any mod. Okay. So if x square plus y square equal to z square, then x square equal to z square minus y square. So this is equal to z minus y into z plus y. Wait, so case 1, x comma y are both even. Can this happen?
Sir, could you repeat?
Wait, just a minute. Okay, so if the meeting ends before I end the solution, please rejoin last time. These are the three possible cases.
This is the last problem for today.
I think so. Yeah.
And you won't
I
be
had
taking any classes.
no. Khatam. Bye.
Why?
Today I have college. I had holiday, so I
Okay.
taught you. Now I have college again. I don't have time. Anyways, uh, so these are the three possible cases. Acha, so if both are odd, if x, y are both odd, what happens? X square is congruent to 1 mod 4 because x is odd, and y square is congruent to 1 mod 4 because y is odd. Now if we add them, x square plus y square is how much? Z square? Z square is congruent to how much? 2 mod 4? Can this happen?
No, it cannot because a perfect
No,
square
sir, it
cannot be
can't
2
happen.
mod 4.
Yeah. So both odd case is eliminated. Okay. Now if x and y are both even, x equal
Yes, it is
to
possible because the sum will
2m.
be 0.
What?
It is possible
And he told
because
that it is possible.
Wait. X square plus y square is how much?
z square.
4m square plus 4n square equal to z square. So this can be written as 4 into m square plus n square. So z 2 divides z basically. Right. Z is also even. So x, y, z, all of them are even. If x and y is even, then z is also even. This is what I prove. Right. But in our modified question, we are only dealing with such pairs, na, where the GCD is 1. Because other cases, I have just taken here, you can multiply n and get them. NA, NB, NC. This is also a solution. So n equal to 2 के लिए 2A, 2B, 2C is a solution if ABC is a solution. So this case is also eliminated. I am not solving this case. Where is the case? Huh. Both even case also gone. Only this case is remaining. Okay. Now x square equal to z square minus y square. equal to z minus y into z plus y. Okay. Now, uh, are these two individually squares?
No,
No,
sir.
na? Like 6 square equal to 4 into 9. These two are squares. But 6 square is also equal to 3 into 12. These are not squares. So in general, I cannot say that these two are squares. Okay. So suppose G equal to GCD of Z plus y and Z minus y. Okay, so Z minus, acha, by the way, x is even. Let x be the even guy and y be the odd guy. Forgot to tell you.
Can
Okay.
you explain this please once again? I'm confused. I got confused.
So we eliminated these cases now where both are even
Yeah.
and both are odd. So only one case remains where one is odd, one is even. So let x is even, y is odd. Okay. Got it?
Yes.
Okay. So if x is even, y is odd, and then z is also odd now because z square equal to x square plus y square. This is even. This is odd. So their sum is also odd. So z is also odd. So z minus y is even. Z plus y is also even. Okay. So this GCD is at least 2 because 2 is clearly a common factor of these two things. Okay. Now see, G divides Z minus Y. G divides Z plus Y. So G divides Z minus Y plus Z plus Y. G divides 2Z. Similarly, G divides 2Y. Okay. But if G is a number which divides both Z and Y, then we also have this na ki GCD of Z comma Y equal to 1 because all the numbers are uh, relatively prime. That was our special case. So G equal to 2 here because any higher number will divide both Z and Y. Okay,
Yes, sir.
got it? Okay, acha. Okay, so now if suppose P square equal to U into V and GCD U comma V equal to 1, then U and V are perfect squares. You can observe this using fundamental theorem of arithmetic, and homework is prove this lemma. Prove this lemma using fundamental theorem of arithmetic. So here we have got Z GCD of Z plus Y and Z minus Y is 2. Okay. So if we cancel by 2, we will get the perfect squares only. Na? What I mean is Z plus Y into Z minus Y equal to X square, which is of the form 4K square because X is even. And their GCD is 2. So here I will get 2m into 2n equal to 4k square. 2 to 4 cancel. So m comma n equal to k square and GCD of m and n is 1. because
we
the
prove that lemma and we get it, right?
yeah. So z plus y I can take as 2r square. So GCD of z plus y and z minus y was 2 na, and once I have cancelled these two, m into n is some square and their GCD is 1 because I have cancelled away the highest common factor which was 2. So the remaining bit is relatively prime. So uh, so these are squares using this lemma. You have to prove this lemma. But for now, assume that this is true and take these solutions. Okay. Z plus y 2r square, z minus y is 2x square. So now we are more or less done actually. Okay. So and GCD of r comma s is 1. So now if you solve, you will get y equal to r square minus s square, z equal to r square plus s square, and x equal to 2rs. If r, s are both odd, then what happens? Then y comma z are both even. Okay, because odd minus odd is even, odd plus odd is even. And we excluded that even case, which was the case 3, I think. No, not case 3, case 1. That both are even. We cannot take both even. So R and S cannot be both odd, and R and S cannot be both even because their GCD is 1. So that is no chance only. So what is the final solution? Final solution is of the form x equal to 2rs, y equal to r square minus s square, z equal to r square plus s square, such that GCD of r comma s is 1 and r s are of opposite parity. Means one is odd, one is even, like this. Okay. So this is our solution for Pythagorean theorem. So what is the solution? You just put values of R and S such that these conditions hold and you will get new Pythagorean triplets. Okay, you can try for values of R and S at home. Exercise. Try this at home. Try putting values and generate new solutions.
Sir, could you please explain what is parity just once?
Parity is just odd even.
Okay, sir.
Okay. Like what is the parity of 1 odd? What is the parity of 2 even? Bus. There is nothing to think about here. It is just a
Okay, sir.
name given. There is nothing fancy like that. Okay. So just try this. Try putting some values and try making some Pythagorean triplets. And final bit of advice is, like here we used modulo divisibility, GCD analysis, everything we use now. So many things we use. So for any general Diophantine equation, use all the, not all actually, use whatever tricks you have learned. Okay, like there are many direct questions in number theory in PRMO, RMO, IOQM, etc. Which you can solve using modular arithmetic or divisibility. But there are a lot of Diophantine equations, and to solve the Diophantine equations, you have to know this modular arithmetic, you have to know divisibility. Okay, so these things also help you in solving Diophantine equations. So use whatever you have learned in the first part of these lectures to solve these Diophantine equations. Okay, and solve examples, read examples, get exposed to more tricks. Okay, so like I can never do justice to Diophantine equations in one lecture or even one course or one semester. So you have to self-study, and I just give you a direction. You know modular arithmetic, you know GCD, LCM, you know divisibility, fundamental theorem, you know all these. Now solving different Diophantine equations is just application of this. So in what ways can you apply that? You have to see questions, you have to solve them, and that is the only way. And I will send you books in the group, read them, see previous year questions, etc. That's it. Okay, so my class ends.
Thank you for the last lesson.
Thank you, sir.
Welcome. Acha, so I have a meeting from 5 in college. Bye bye.